Thank you very much for the invitation for the workshop. So I'll talk about using machine learning for 3D imaging. It's quite related to what Ian said, but it's a different wavelength to use. It's about optical tomography or imaging three-dimensional objects with optics. Some very similar, a lot of similarities, but also a lot of differences. So it's kind of interesting to kind of see it from different points of view. So I'll start by reviewing optical diffraction tomography, which is, I could do it faster than before because of what we just heard. And then I'll talk about three different ways that we've explored for applying learning techniques to the problem. And the problem is well matched to machine learning because what you do in tomography is look at 2D projections of a 3D object. So inherently it can be ill-posed if you don't have enough projections. It can be noisy, it can have defects because of the way you detect the fields or whatever you detect. So inherently machine learning can be a way to find ways to correct some of these problems. And if I have time in the end, I'll talk about an implementation that I think is kind of different and interesting for doing diffraction tomography. Okay, so diffraction tomography, the idea is you have a 3D object in the middle there, and then you illuminate it with an optical beam, a laser beam in this case, that's collimated, and some of the light gets transmitted and gets scattered, and that gets detected on the camera. So the difference between what we do and what Ian talked about is that we have the option or the luxury to use a reference beam because it's very coherent, it's a laser. So we can record a hologram from which we can extract the amplitude and the phase separately, and we don't have to do this Kersberg-Saxton or FinUp stuff to get the phase. Even though in the end I'll show you that we use neural networks to do that as well. Okay, then when you change the angle of illumination, basically you're looking at a different projection, so you gather a large number of these projections, and the goal is to put them back together and get a 3D shape. So Emil Wolf, the famous Emil Wolf in '69, I think, had a very insightful paper. So I call this the Wolf transform, the method to inverse it. He noticed that if you illuminate an object, a 3D object, you can think of the 3D object as consisting of a superposition of 3D gratings by taking the 3D Fourier transform of the three-dimensional function that describes the index of refraction. So assuming no multiple scattering, you can think of a plane wave being scattered by each of these gratings, and then you can detect its amplitude and phase separately. So each measurement you make on a pixel on the camera tells you about the strength and the orientation and the frequency of this grating. And multiple gratings representing the 3D shape do their own diffracting. So basically in the camera with 1 million pixels, you measure 1 million gratings. And you change the angle of illumination and you probe different gratings. And in the end, when it's all said and done, and you've measured all these gratings, you can do an inverse 3D Fourier transform and get back to the index distribution. So that was what Wolf did in this paper. And of course, this is what now we always do. The setup looks like that. It's a holographic setup. So there's a signal beam that illuminates the sample. The samples we look at, in this case, are usually things like cells, which are largely transparent, but they have index distribution. Like normally the nucleus, for example, has different index, higher or lower, depending. And then the scattered field from that, or the transmitted field from that, is interfered with a reference beam, and then you can extract the phase. So this is already the phase of the object. And in doing this Wolf transform, you can get very nice reconstruction. This is a cell that's about to go division, and you can see it has 2 nuclei, and these are lipid, and you can see, if you look carefully, you can even see other organelles, like mitochondria. And this is a 3D printed transparent medium that you can also do it nice. So the resolution here is typical microscopy, maybe 200 nanometers X and Y, and you get nice shapes. So given that we get these beautiful, nice images from a algorithm that Wolf presented so many years ago, and there's variations on it called RITOF. There's different variations on that. Why do we need to use machine learning? Because there are several aspects in the traditional Wolf transform that are not taken care of. For example, multiple scattering. The whole idea there is each grating, you assume that each grating that makes up the 3D object scatters light, but that light does not get rescattered, which for strong index variations is not true. Then you have the missing cone problem, which means you don't collect all the information, or you don't make all the illuminations, all the scattering. I'll show you, the last example I'll show you is to go to get the phase from intensity directly without doing this holography thing, which I think Ian just talked about as well. Everything normally people do is scalar. You assume the one polarization for the field, but this is not true in general. Of course, it's a vectorial problem. Depending on the intensity of the laser, could be we have nonlinearities. You can also handle them, denoising, etc., etc. So let me first talk about the multiple scattering problem. So the multiple scattering problem means, is what I just said already, that as the light propagates through a 3D object, when it first meets the entrance part of the object, that distorts the field, so that's a scattering event, and then when it gets distorted further downstream, that's multiple scattering. So if you have an object like this, these are 3 cylinders, or 3 bits if you want. If you go through this Wolf transform and all that, and if the 3 objects are oriented like this, you get a very nice reconstruction. If you tilt them so that the light propagates across the cylinders, like here, the reconstruction gets strongly distorted. Why? Because the algorithm assumes that the plane wave, that the second cylinder here sees a plane wave. But it doesn't see a plane wave, it sees some sort of cylindrical wave because of the first one. And this causes these problems. And the problems are of 2 types. You get some index values in places where you shouldn't, like this gray area in between. And also the index of refraction that's being guessed is incorrect. This is the correct one, and this is incorrect. The ones farther downstream get wrong. If we use this technique, which I'll describe to you next, which we call learning tomography, you can resolve this problem. So the idea is an iterative reconstruction method. It's the holographic setup I showed you before, where we measure the phase. And what we have in the computer, so what you see down here is something that takes place in the computer. So you simulate the input wave coming into the sample, and as it enters the sample, it gets distorted and reaches the output. And the simulation keeps track of the complex field, so it has the phase. So at the output then, we can compare the measured phase with the phase that's predicted by the model. And the model contains in it the index of refraction of the sample. So the goal now is to optimize, minimize this error by choosing the right index of refraction. So we use as a propagation model this beam propagation method, which takes the cell here and cuts it down like in little pastrami slices, very thin slices. Each slice has a little bit of a phase modulation, a little bit of Fresnel diffraction, and then again and again and again. Typically in our simulations we do a few hundred, maybe 400 or 500 slices for a cell about 10 microns thick. So this is the beam propagation method. And if you want to write the diagram for what I just told you here, but that you take the sample the 3-dimensional sample you'd like to image, and you cut it in thin slices, then in each slice, 2 things happen. One is the phase modulation. This circle delta phi. And then some diffraction, which is represented by these black arrows. And these are just fixed kernels of the Fresnel diffraction operator. And that's the next slice and the next slice. And you get to the edge of the to the detector, so to speak, where you have the experimental measurement, you compare the 2, and you use this to modify the phase. So this, looking like a network, like a neural network, allows us to use this error backpropagation method that we normally use in multi-layer networks to modify not the weights of anything, but directly the phase or the index of refraction of the 3D object. So this works quite nicely. This is a HeLa cell, type of cancer cell. This is the XY, one slice in the middle, and this is the YZ and XZ slices. And you can see you get nice reconstructions, and then this is for 81 projections. This is using the radon transform, which assumes geometrical optics, no diffraction. And then this is the Wolf transform, which also is not as nice. And then particularly as you go to fewer and fewer projections, they say just 6 projections, this blurs, which makes a lot of sense because the Wolf transform, you get it by taking the 3D Fourier transform of the frequency components that we measured. So the fewer projections that we have missing frequency components, so it's like low-pass filtering in 2D. Whereas the learning technique, because it looks for a consistency between data measurements and prediction, it finds a better solution. That's kind of an element of the learning. This is another example showing how multiple scattering is taken care of. In this case, the experiment had 2 yeast cells, one after the other. Here the horizontal distance is Z along the light propagation. And then there were 2 cells. So the Wolf transform here got confused because, again, because the light scattered from the first is not a plane, results in an illumination of the second cell that's not a plane wave. So it looks bigger and lower index, but then this learning tomography, because it assumes multiple scattering, figures it out. Okay, so now this is we call it learning tomography. It's been out for a while, so applied it for many different things. I'll show you in the end, if I have time, another application. So it looks like a network, it smells like a network, but it's not really a network because it's just a structure. You might call it a physics-inspired network, but because directly you impose the wave propagation in the structure that you optimize. And there are no weights. It's the index itself directly that's being optimized for. What I'll describe next is an idea for using neural networks to address the missing cone problem. And what's the missing cone problem? If we have a plane wave here illuminating the scattering object, like the cell, we have a lens with a certain numerical aperture that captures the scattered light onto the detector. But there's a lot of light that it does not capture, like reflected beams or beams scattered to the side that go to the wall of the laboratory and so forth. So all that light is missing. For example, the light that's reflected right back represents very high frequencies in the object along the z direction, along the optical axis. So at least in the geometry that we've been using, that's not captured. What's the net result of that? That instead that the Wolf transform gives you this kind of reconstruction, and the error is big, particularly in along the z direction, along these missing cones, because in the spatial frequency domain you don't capture these high frequencies along z. So I'd like to fix that. So one way to fix that, you take the experimental measurements, take the measurements off of the detector, and enter it to a neural network, which will give us the correct index of refraction, accounting for, or guessing, or anticipating these missing frequency components in 3D. We could put them directly into the network, but we don't. Instead, we go through the Wolf transform and first get an estimate for the 3D index distribution with the missing cone, with the missing frequencies. And now that becomes an input to the neural network to give you something that kind of anticipates the missing frequencies. For those of you that know, people, including some people in the back there, like George Psaltis, have done this in 2D, where you can do super resolution. You have low-pass filtered image. You can train a neural network to guess the high resolution. And also, Oscan here did similar work. So this is the network we used. It's a UNet that also Ian talked about before. It's a res net, meaning What the unit does is try to calculate the difference between the initial thing we feed it to, this Wolf transform, or Ritov, it's a variation of the Wolf. So the network itself calculates the difference and gives you the truth. The question now is, what is the ground truth? How do we get the 3D distribution of indexes is chicken and the egg? Because we're trying to do tomography to measure these things, and then we don't have the true value. So one answer is to do what Ian did, make a model and create a database from the virtual models. So for red blood cells, that's relatively easy to do because red blood cells all have the same shape. It's shown here. It's a little bit of dimple thing. And inside is uniform. It doesn't have a nucleus. It's just blood. It doesn't have any structure. And with a few parameters, you can define its shape and vary its shape. So you can create a large database by having different parameters into the shape of the red blood cell. And then use some method for going from index to field, for example, discrete dipole approximation or COMSOL or something like this. And then you can create a database of what would the scattered field look like under different illumination conditions. And that becomes the database. So that's what's shown here. By changing the angle and rotating the sample and so forth, and using discrete dipole approximation in this case, you create multiple 2D measurements as you would have done in the experiment, and now you have a database to work on. And we do it within the numerical aperture of the optical system, which means the data that's generated virtually also suffers from the missing horn problem. So the reconstructions that we get through the Wolf transform, or his cousin, the Ritov transform, looks like this, whereas the truth should be like this. This is an XY slice, XY slice towards the middle of the cell, and there the cell should have been, the index should be uniform. It's just the index of the blood, because there's blood everywhere in the middle of a red blood cell. And same thing for XY. So what the network is called to correct is this. In other words, it's trained with this virtual database, and now when we bring a true red blood cell, we should guess right. And this is experimental results now. So the network is trained to this virtual database with these phantoms. And then if you just do the Wolf transform, you get these reconstructions, which are show that there's a hole in the middle, which red blood cells don't have a hole in the middle. And however, this network does much better, does actually quite well for red blood cells. So that's one approach, to build a network that learns from phantoms, from synthetic data, and you create a database this way. Now, if you go to more, maybe perhaps this can be extended to more complex type of cells, cells that have a nucleus and organelles and so forth, and you can create a synthetic database of 3D objects of a certain class of interest and go that way. So that's one way to go. And we're not really pursuing that, to be honest, but pursuing it for a particular type of cell, again, different family that's also kind of suitable. What I'll show you next is something I think more interesting, which is a way not to need samples at all. You can do it without examples. So you just have, somebody higher up, of higher authority, that tells you whether you're doing well or not without actually giving you the answer, the exact answer. So the idea is to use an iterative reconstruction, which is similar to the learning tomography I showed you earlier. So you have an index of refraction you're trying to guess from the experimental measurements. And you need a forward model, which before I showed you is BPM, to predict these measurements. And in the previous, the BPM, the forward model contained inside it the index of refraction, and we directly minimized for that. In this case, we're going to use a neural network instead. So we're going to start with the index of refraction, and we're going to go from index to field. This is like COMSOL, or, the model could have been COMSOL, but instead we'll use a neural network to go from index distribution to the field. Then you compare that to the measurements, and then go back. The question is, how do we train this network? Again, we have the same problem. How do we train this network? Again, we can try index distributions that somehow randomly chosen, and to get enough of them that will get a network that generalizes, that can mimic COMSOL by examples. But so basically, the teacher could be COMSOL. You put in different indices, you measure different fields, and you train a network to do this. That would be very, very difficult for a number of reasons. So this is what I described here. You have a deep neural network, and if you could have the network predict the field, this would be E hat, and you have some ground truth of what the field should look like for this index distribution, you can do normal training of some sort of network to do the job. But this is very difficult because these numerical techniques are heavy, and also you have to have some sort of an understanding what is the family of objects that you're going to focus on. What we do instead, we use as a loss function, instead of using the difference between what the network produces and what COMSOL gave in this case, we use instead what the network produces and what Maxwell said it should be. So basically, we have a prediction of the field, and if this field was exactly correct, given the index distribution or the dielectric constant distribution of the object, or this particular instance that we're trying to estimate, if this is correct, and we plug it into Maxwell's equations, then it should be zero, because Maxwell's equations are Maxwell's equations. So it should be zero. If it's not zero, we call this the loss function, and then we train this network to do the job. So now the fact that we know that the data we're dealing with and the problem we're asking is an electromagnetic problem, we can directly apply this constraint that Maxwell's equations should still apply on one of the quantities that we're guessing, which is the electric field. So here's an example of this. If you have something like a lens, this is a very small lens, it's 2 microns. So the index of refraction here is glass, and then outside is air. I think it's water in this case, water. So if you do the curl of the E field, this is computing using the beam propagation method, which is a relatively inaccurate method. And then this is the other term that's in this equation. This is the wave equation, not really. It's derived from Maxwell's directly. There's a residual, meaning BPM is not accurate, and this is the error. And you can use this error. So if you instead use COMSOL, this term, the first term here, the curl of the E, is this, and the other term, epsilon times Z, is this, and the two match pretty well, and you get zero. That's beautiful, because you have here the technique says, okay, I can tell whether I'm using BPM or COMSOL. And I want the network to be more like COMSOL than BPM. So this is the network. So you put the index distributions that are in your family of objects. The network predicts the slow varying envelope. Then we add the incident field here to create the full field. That same index is also contributing to the loss function, because the dielectric constant is part of the loss function in the Maxwell's equation. And you calculate that, and using error backpropagation, we can train the network to behave like a high quality, whatever, hopefully a good quality field calculator given an index distribution. So here's some results again for the lens. So this is 2 examples, left and right, just 2 examples of 2 different lenses. This is the lens shape, and this is the network, the field produced by the network. This is the real part, and this is the ground truth. Ground truth is COMSOL, and this is the same thing for the other lens. So that's 2D simulations. It also works in 3D. Here's a phantom again. There's a phantom supposed to be a little bit like a lens. There's 2 indices inside that are a little bit higher, and then yeah. So this is the 3D object, And now this is the real and the imaginary part produced by the object. And this is again the Maxwell net, or this idea of a network that's trained using Maxwell's equations as a loss function. And this is the same thing done by COMSOL. And these look very similar. And quantitatively, the difference, the color here is 0 is red, and for the imaginary part, blue is 0. So this is pretty much low error. So at least at phantoms it works nicely. And what's the advantage? These are 2D phantoms, which I showed you briefly, but this is the 3D phantom I just showed you. Now, to train this Maxwell net for the 3D phantom, it took 15 hours on a high-end GPU. So it takes a while. But the inference is, on the same GPU, 45 milliseconds. It's really fast for a 3D object. Even BPM, any of those other simulators would be orders of magnitude slower. The COMSOL, for example, is 4 orders of magnitude slower. And this 15 hours is daunting, but the good thing is that you're learning Maxwell's equations, and they will not change over time, I don't think. The physics, the laws of physics may gradually be drifting. There are some people that argue this, but at least we don't think so. So that means that if you train a network to calculate the field based on Maxwell's equations for a class of objects, you can imagine creating a library over the years and so forth, and then developing something that can doesn't need to be trained so much all the time. We also tried this in experimentally. So this is a very initial experiment. We published this, actually it was accepted. It should come out in a few days, or at least, so the publication was accepted and to come out soon. So this is an experiment of a single bead, a polystyrene bead in water, and the illumination was, it was illuminated in a circular pattern, at different angles going around the top. And this is the normal Wolf transform reconstruction, which has the missing cone, and because it's stretched out in the z direction because of the missing cone, and the index is underestimated. Whereas again, this Maxwell net did very well to predict it. I guess I messed up here because I didn't tell you how we use Maxwell net to do ODT, but we use it in this iterative scheme, in this scheme. So in this scheme, we use this as a forward model, and then we backpropagate through this model to directly change the index of refraction. Okay, so do I have 5 minutes left?
Yeah.
Okay. So I'll tell you something also related to tomography. It's a little bit different idea. This was, the idea is to put 3D objects in a microfluidic channel. And if you put an object in a microfluidic channel because of the non-uniform velocity field, the object normally feels forces that make it rotate, and it puts some torque on it. And this rotation now can be used as a way to present different views of the object to the camera. So you can do tomography this way. So the idea is we launch a single cell, or not multiple cells, but single cell at a time. And as they propagate in the channel, because of this Purcell flow, this parabolic profile of the velocity, if it's not at the very middle of the channel, if it's a little bit off, it will start rotating. And when the microscope looks at this, it will see different rotated versions. And if you make holograms like we did before through this beam splitter, then you record that, make a hologram. We estimate the phase. We have a neural network of cells described in a second to estimate directly the phase, because extracting the phase from a holographic recording takes it some time, because you have to do an FFT, pick the right term, bring it back to the middle. All that actually is consuming. Of course, the neural network does it automatically. Then we apply this learning tomography I showed you earlier, and then we get the reconstruction, the 3D reconstruction. So this article of ours is actually also accepted in Nature Photonics, about to come out in a day. And the reason it got accepted there, I think, is because we're able to estimate the index of refraction with very good accuracy. 0.001 accuracy index of refraction. And this allows us to look at the nucleus of the cell and the nucleus, which is the stuff inside the middle of the cell that contains the DNA, and organelles such as mitochondria and so forth, and differentiate them from their shape, but also from their index values. So that's quite interesting because now neural networks is used in this scheme, or in two ways, in this learning tomography, but also here to go from intensity measurement to phase. So when people say phase from intensity is unique, holography is also phase from intensity, right? You record the intensity pattern, you extract the phase, but this is more direct. So that's what's shown here. You measure the holograms, and without you have the hologram, meaning you have the a square plus r square plus 2ar, etc. That whole thing is on the camera, but instead of taking FFTs of it, you put it in a network that's trained to extract the phase. But now the database comes from taking those same holograms during the training and extracting the phase and measure them. So now you can build a database of intensity to phase and then use the network. Again, I think George Barbastathis, I think, did things like this, of course, I'm not sure exactly the same, but very similar. And that is, the speed up again is huge. So here I'll show you a little bit of these images. So what you see here, you'll see this is a microfluidic channel, and this is a cell, you'll see it here traveling up, and this is a different cell traveling up. And what you see in the bottom is, in real time, this neural network extracting the phase. So it's very important because if you imagine this microfluidic platform, the idea is to have this high throughput. I'll come back and explain this. High throughput. So you have, hundreds of thousands of cells. So if you want to accumulate everything, it's going to be difficult. So you want to be able to, in real time, measure the phase and do something. Pick cells that are suspect, is cancerous, no cancerous, so do something, rather than just accumulate big database. So let me see what happened here while I was talking. Okay, so go back. Okay, so here you see the cells going into the fluidic channel, and you can see, you can almost see them rotating. And this is the corresponding phase, which has this kind of illusion of rotation. It's not really, you don't see rotation here, but it looks like it's rotating. So the extracted phase, as the cell rotates, you see different phase delays. And I'm going to let it run again now. So what you see here now is the index distribution that's produced by this learning tomography. And then we have a different algorithm now that does clustering of voxels of the same index of refraction. And this clustering, once it runs its course, actually pulls out the shape of the cell. And you can see here, these are two different types of cells and different types of cancer cells, so different cancers. And you can see the index distribution, which is a histogram of the index distribution down below. It's different, first of all, so that alone would be interesting, just to differentiate between those two. You can use the histogram. And then the nucleus distribution and the non-nucleus, in other words, the stuff that's in the blue and in the red in the cell, is different from one type of cell to the other. In the more recent work, we also look at more fine organelles using the same idea. The idea is based on index 2. So this leads to, you can do microscopy based on label-free imaging. Again, people like George and stuff have been talking about this for a while. And there's a lot of advantages to do imaging, and also Oskan here. He talks a lot about this business of label-free imaging. He was supposed to be here, he told me, but I don't see him here. I think he's flying in from somewhere. From Greece, actually. I'm from Greece, I don't know. Derek's vacationing in Greece, so this is a good thing. The nice thing about using label-free is you can avoid bleaching, you can avoid blinking, chemical modification by introducing. There's a lot of different things that you can argue that it's a good thing. And in the end, you can combine it. You can have dual mode. You can have fluorescence and this index measurement or phase measurement. To summarize my last slide then, I told you about this Wolf transform. If you can get images with that, that's good enough. That's the best, because it's fast and no training required. It's not as fast as a neural network, by the way, but it's fast enough. It's single shot, not iterative. But it has this missing everything else, you know. Learning tomography takes care of this multiple scattering, so you can have objects, but not reflections, by the way, just forward scattering, at least not yet. And it still has this missing cone problem, by and large. The TomoNet, the idea of using this red blood cells where you can have a phantoms virtual database, it does extremely fast inference and solves the missing cone problem, for example. But you need to be able to create a database from phantoms. The Maxwell net does everything, in principle. You can have polarization, you can have nonlinearities, you can have reflections, everything. You just have a network that says, I put an index distribution in, or something else, the chi3, whatever else you have, and then you say, can I produce the field? The difficult thing about it can be very heavy computationally. So the hope is that you'll have some transfer learning. You know, it's what you learn from one database, it may transfer to another, or you can create a library of objects that then you can look upon quickly or something like that. So you can create a competitor to COMSOL for this sort of thing. So acknowledgements, you know, everything I've talked to, this fellow Juan Lim, who's now in Microsoft in Cambridge, England, was a big contributor. Amir Hossein works on this, also works on this Maxwell net. Carlo, all these guys work on that part. Alexander Goua, Yannis Papadopoulos, and Morteza Sore did the early learning technology, learning tomography part. And I have two collaborators, Michael Unzer and his then postdoc, Ulukbek Kamilov, who's now a professor himself in Washington University, Washington in St. Louis, and Pietro Ferrari, with whom I were doing this microfluidic stuff in Napoli.